Hello there, and welcome to the very first video in my calculus series. In this introductory video, I'd like to provide you with a bird's eye overview of the subject by exploring a simple but real-world scenario that will create context for all that we learn moving forward. So without further ado, let's begin.
So here's a scenario. I do this with my students on the very first day of AP Calculus. So here we go. You leave your house by car to visit family. 4 hours later, you arrive at your destination, a distance of 200 miles away. Your job is to make a sketch of your distance from home over the 4 hours. So when I give this to my students, we have some varying types of graphs that crop up. So I'll kind of give you a little highlight. So the most typical graph I see is the students draw this. And this straight line graph that terminates at the point 4, 200. So it's understood that time is on the x-axis and distance is on the y. Another typical graph is, well, let's just kind of do this. We're traveling along, we stop for a while, and then continue along. So I've had this type of scenario, and then perhaps one other one. Let's see, here's a student who was driving on his way to the family, but then forgot something at home, had to return home, and then had to drive straight there. Okay, and then I asked the students to be prepared to describe their journey. So, and this is interesting because when they actually have to describe it, they find that there are a few limitations in their graphs. So in this very first instant, the student soon realizes that they're in their driveway and they shoot out of their driveway, suddenly attain this speed, which they maintain throughout the whole 4-hour trip. So they don't slow down. They don't stop at traffic lights. They don't even slow down to get on the highway. They go at a constant speed the whole time. And when they arrive at their destination, they kind of just stop dead in their tracks. And they soon realize that what they're actually doing, if they're covering 200 miles in 4 hours, they're traveling at a constant speed of 50 miles an hour. So you could get that by dividing 200 by 4, which of course 200 is the rise of this graph and 4 is the run. So you're just working out the slope. In the next scenario, once again, traveling out at a certain speed from 0 to whatever that speed in no time whatsoever. At this juncture here, they just stop dead at the rest stop or wherever they are, and then they pull out of the rest stop at some bigger speed because they're kind of making up time to get to their destination. So now you can see the limitations of these graphs, and the students soon realize that you need to have a little sort of more smoothness to the graphs, a little more curvature to make it realistic. But we will start with this scenario because it's a nice sort of more straightforward way to delve into the concepts of calculus. So let's take the scenario where we stop at a rest stop. What information from this graph, this is a distance time graph, the question is what information can you gather about the car at t equals 3 hours? So this is important because where you see there's something that's very obvious. The very obvious piece that you can read right off the graph is that it's 120 miles from home. And that's if you just follow this at t equals 3 hours, you can read off that we're 120 miles from home. But there's something that maybe is not so obvious. Give you a second to when you pause the video if you want to try and figure it out. But it can be interpreted from the graph, and we touched on it in the slide before. And that is the car is traveling at 80 miles an hour. So where does that information, where does that 80 miles an hour come from? Well, if you think about it, at this point here, at the 2 hour mark, it was 40 40 miles away from home. And then at the 4-hour mark, it was 200 miles from home. So it traveled a distance of 160 miles. And it did that in a space of 2 hours, which is this. So that when you divide 160 divided by 2, you realize it's traveling at 80 miles an hour, which is basically finding the slope of that line segment. So now see if you can pause the video for a moment and make a sketch of the speed of the car over the 4-hour period. So we know that all along here, the car is going at a constant speed because we see that it's a straight line and the slope along there is 80 miles an hour. So this should be your speed versus time graph. I'm going to ask the same question. What information can you gather about the car at t equals 3 hours? Well, the one obvious point is that it's traveling at 80 miles an hour, and that's the y-coordinate corresponding to the yellow dot when t equals 3. But the next piece of information isn't inherently obvious, although a little calculation can get you there. And that's that the car is 120 miles from home. So where does that come from? Well, if we think about the first hour, it's traveling at 40 miles an hour. That means that it obviously covers 40 miles in that first hour. And the important thing here is to realize that that calculation is just the area of that rectangle, the area under that red line segment. In the second hour, it covers no distance because you're at a rest stop. And in between hours 2 and 3, you're traveling at 80 miles an hour. So once again, 80 times 1 is 80 miles that you've covered. And that would be true if you were traveling for 2 hours at 80 miles an hour. That area would correspond to the distance traveled, 160 miles. So this interplay between the two graphs is the essence of calculus. So when I say the two graphs, the distance time graph, and this distance time graph could also be population versus time. It could be any quantity versus time. And if we work out the rate of change of that quantity, in this case speed, these two graphs are intimately connected. And the first half of calculus is all about moving from the left graph to the right. It's differential calculus, and it's all about the slope. We've been dealing with slope of line segments, but it gets more interesting when we have curves. And the second half of calculus is reversing the process. That's integral calculus, and it's talking about the area under a curve. So for one more scenario, if we were thinking, oh, I don't know, in half an hour. Well, in half an hour, we know that we are 20 miles, right, from home. Okay, and and we know that our speed is 40 miles an hour. But if we go here to the half-hour mark, this is half hour, and we're going at 40 miles an hour, we know that's our rate of change. All we need is the area of that portion. Half times 40 is 20 to tell us that indeed at half an hour we're 20 miles from home. So that is the overview of the whole unit on calculus. The first half differential, which we'll be delving into more deeply now, and we'll be putting off integral calculus to a little later. All right, what if your distance time graph was the following? So we have here slightly more realistic situation, not entirely, but at least you're not shooting out your driveway to 50 miles an hour in 0 seconds. You're starting off slowly and you're picking up speed the whole way. Admittedly, you're not slowing down or stopping until you get to your destination, and that, a little bit unrealistic there because you don't slow down in order to arrive. You just, I don't know, crash into the front driveway. So question again, how could we find the speed of the car at t equals 3 hours? So we want the speed at t equals 3 hours. Can we do it now that we have a curve and we don't have a straight line segment? Well, you could argue that you could find the speed by just looking down at your speedometer, but seriously though, this is such an important concept with many applications where there's no speedometer at hand. Think of a falling object or even something like the speed of a planet at a point on its orbit. So we really have to be able to, calculus really addresses how to find the speed at or the rate of change at a particular point on the curve. So it turns out that we already have a gut instinct for this, that the speed is going to be found by finding the slope of the curve. But what is the slope of a curve when we've only ever thought of slopes of straight lines? So the slope of the curve is in turn the slope of the tangent line. And what is the tangent line? There it goes. The tangent line is a straight line that touches exactly only once at that point. You will recall, just to remind you maybe from geometry, that a tangent line, if you had a circle, a tangent line, let's see, would be a line that touches down on the circle just once, not the best looking line that looks like it goes through twice. That's the tangent line. And that to be distinguished from what's called a secant line, which passes through the circle at 2 points. One way to think about the tangent line is it's the line that if the circle rolled down this hill, the hill would always form a tangent line to the circle.
Hello again. So that brings us to the end of this introductory overview of calculus. In the next video, titled The Tangent Line Problem, we take the example of the distance time graph just introduced and explore how to find the slope of a curve at a point. If you found this video helpful, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.